Okay, so this is just going to be some biochemistry basics, really simple stuff on looking at a drawing of a molecule and then being able to understand what that means as far as making a chemical formula or something like that, just understanding a molecule's structure based off a drawing of it. So this first model is ball and stick model, and these are different things. This middle one is glucose, and this is a fatty acids chain down here at the bottom. So we have a ball and stick model, so like the blacks are carbon, red is oxygen, white is hydrogen. And then we can see Lewis structure, and in a Lewis structure you have every single one labeled. And then in the line drawing, it really tries to give you the 3D shape with drawing as little as possible. So when we look at this pentanol, there are actually, like in the Lewis structure, carbons and hydrogens here, but they're inferred. And same with the fatty acid chain, there's a lot less going on. So when there is special stuff, you're able to see that. So let's look at two examples here. So this first one's a disaccharide, and we kind of know because the structure of a carbohydrate has this hexagon type structure. And then we can see here that they're bonded together by an oxygen. That's called a glycosidic linkage. And so basically in a reaction, and the reaction to split these apart would be hydrolysis. And so you would add water to this, and that would break it and put an OH group on one side and an H group on the other. Oh no, it'd put two OH groups on each side. So it would cancel out and be OH over here and OH over here. Because we have two hydrogens and two oxygens. Oxygen, 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 oxygen. So that would be hydrolysis, and then the same thing in reverse would be dehydration synthesis. So we pull the water out, and then one oxygen remains, bonding the two, creating a disaccharide. The second one is a Parcel fatty acid chain, just looking at the tails. So it doesn't look like much, but because at each point on this we know that there's a carbon, and then that means there's a hydrogen above and below, and off of each point there should be four bonds. And if there's not 4 lines drawn off of it, then we show imaginarily there are lines drawn off that have hydrogen. So now from this point there is 1, 2, 3, 4. And so right here with the double line, that's a double bond. So we really have C bond, double bonded with carbon, which this is an unsaturated fatty acid chain, which causes the kink and gives a lot of unsaturated fats its properties, such as being liquid at room temperature. So this is a thing of caffeine, CAFF, of caffeine. And so now we kind of have an understanding of what's going on here. We can see that there's 2 oxygens, so I'm actually going to try to get us to write the chemical formula first. So carbons first, we'll count 1, 2, 3, 4, 5, 6, 7, 8. We'll do it again. 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 carbons. We'll go hydrogens next. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Feel like I'm missing one. And then we'll look at oxygens, or we'll look at nitrogens. 1, 2, 3, 4. And oxygens. I can see there's 2. 1, 2. 1, 2, 3, 4, 5, 6, 7, 8. Oh, that's totally wrong. Nope. I wasn't thinking, because we have to take into account all the ones that are not bonded. So right here there would be a hydrogen. Let's see, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10. So I'll write that's really nice. C8, H10, N4, O2. And then down here, that's what we have. So this is the chemical formula for caffeine, just what we wrote. So now by looking at a line structure like this, we can derive the chemical formula for it. And I hope that was helpful.